Alright, so this is the first half of the Chapter 4 review. It only covers problems that are relevant to sections 4.1 through 4.5, and it goes between 1 and 12 on the review. So more often than not, when I do Chapter 4, I break it into two 50-point tests. The first 50-point test is over 4.1 through 4.5. The second 50-point test is over 4.6 through 4.10. Every now and then, there are semesters where I do a test over all of Chapter 4, and if that's the case for your semester, you'll have to watch both videos as opposed to just one at a time. So the first page here has a couple problems of the number ones, and I can do these without algebra pretty nicely. I mean, I can do them in my head, should I say. The first problem, I'm multiplying terms that have the same base. And if you're multiplying terms with the same base, you just add the exponents. And so y cubed times y squared, the y doesn't change, but the exponents get added. And for an answer, I should write y to the 5th power. For part B, for the numbers 6 over 16, I'm going to reduce each of those by 2. 6 divided by 2 is 3. 16 divided by 2 is 8. So in my answer, I'm going to have 3 in the numerator for certain and 8 in the denominator for the reducing the 6 over 16. For the letters, the x's, because we're dividing, I have to subtract the exponents, but the x needs to wind up where the bigger exponent was. Since the bigger exponent's in the denominator, when I do that subtraction of the 5 minus 3, I'm going to subtract and leave the x in the denominator because I always leave the letter where the larger exponent is. So for my answer to this problem, I'm going to write a 3 in the numerator, an 8, and an x squared in the denominator. C is a little bit harder. I need to multiply the exponents of the letters. Technically, the 3 has an exponent of 1, and I need to multiply its exponent by that 4. I could have just raised the 3 to the 4th power and been good with that. Could have did it that way. So first thing I'm going to do is 3 to the 1 times 4, which is 3 to the 4th power. Use my calculator for that. So 3 to the 4th power, and I get 81. So part of my answer is going to have the number 81 from what the 3 turns into, and I raise it to the 4th power. And then the exponent on the x is going to be 8, and the exponent on the y is going to be 16. The next part is a little bit harder. The negatives make it tough. Again, for the letters that don't have exponents, I have to assume they have a 1 and multiply their exponents by 2. For the numbers, similarly, I have to assume their exponents have a 1 and then multiply their exponents by 2. For the x, if its exponent had a 1 and I multiplied it by a 2, I'd wind up getting negative 3 to the 2nd power for the negative 3. For the x, when I multiply its exponent by 2, I'll wind up with x squared. And for the y in the first parentheses, when I multiply its exponent by 2, I'll get y to the 4th. So the first parentheses simplifies to negative 3 quantity squared. And that negative, if I'm doing it on my calculator, absolutely has to be in a parentheses. If I don't put that negative in a parentheses, I'm going to get the wrong sign. So the first parentheses reduces to 9x squared, y to the 4th. And then same thing for the second parentheses. For the second parentheses, if I assume the negative 2 has an exponent of 1 and multiply it by 3, that'll be a good enough way to handle the negative 2. And for the x and the y, I'll multiply their exponents by 3. The negative 2, ultimately, I'm going to have to cube it. The x in the second parentheses is going to have an exponent of 6. The y in the second parentheses is going to have an exponent of 3. And then negative 2 quantity cubed is equal to negative 8. So I'm going to rewrite the second parentheses, have a negative 8 and x to the sixth and the y cubed. The nice thing is neither parentheses has any adding or subtracting, so I could just, to finish up the problem, multiply all the like pieces. So I'm going to multiply the 9 and the negative 8, the x squared and the x to the sixth, the y to the fourth and the y cubed. And when I do that, my answer is going to have three things being multiplied. The first, the number negative 72 for the 9 times negative 8. On the x's now, I'm going to add their exponents and get x to the 8th power. And for the y's, I'm going to add their exponents and get y to the 7th power. So the final answer to part D should be negative 72 x to the 8th y to the 7th. For part E, I'm going to multiply all the exponents by 3 again. So I'm going to go 3 to the 1 times 3 power. I generally wouldn't even show this multiplication. I would have just made it 3 cubed. And then x to the 2 times 3 and y to the 1 times 3. Again, when the letters or numbers don't have exponents, you don't really need to show that multiplication. It probably would have been nicer if I would have just written a 3 cubed in the numerator and a y cubed in the denominator without showing that multiplication. But I have to show the multiplication on the x, or at least do that multiplication in my head, and I get an x to the 6th. I'm almost ready to have my answer. Figured out that 3 cubed is 27. So my answer to part E of number 1 is going to have a 27 and an x to the 6th in the numerator, and it has a y cubed in the denominator. So that's probably everything from section 4.1 that is test worthy. The next problem starts to have things from 4.2, and in section 4.2 I have to be careful with negatives, and I'll add a part C, D, and E to this just to beat this to death. These are just new problems that aren't on the review, but you should be able to do. For whatever reason, when I give a zero exponent problem on the test, and it's one of the trick ones, students make mistakes. So 4 of these problems can be done on my calculator. The only one that I couldn't do on my calculator is the part A, but that's the easiest one because that's just something without a negative sign being raised to the 0 power, and that's definitely going to be equal to 1 for an answer. The next 4 problems, the one that's actually part of the review and the ones I added, I could do on my calculator. So negative 2 to the 0 power is supposed to equal negative 1. This is because that negative, it isn't in a parentheses. This really means negative 1 times 2 to the 0 power, and it's 2 that's being raised to the 0 power, not the negative 2. And if I did this without my calculator, that's how I'd have to think of it. I'd have to raise 2 to the 0 power and get a 1 and then multiply that by negative 1. The next 3 are just important because they could make their way into the test. This negative 2 to the 0 power with a parentheses, this is raising a negative 2 to the 0 power, and I don't have to multiply it by negative 1. The negative 2 is being raised to the 0 power, whereas in part B, only the 2 is being raised to the 0 power and not the negative part. Similarly, D and E are just repeats of B and C with a different base. The part D, if I did negative 3 to the 0 power, my calculator is going to tell me that this is negative 1 because it's only the 3 that's being raised to the 0 power. Again, this part D is really negative 1 times 3 to the 0 power. Only the 3 is being raised to the 0 power. 3 to the 0 power is 1, and negative 1 times 1 is negative 1. But part E, again, not from the review, but something you should be able to do on the test, is going to be 1 again. So when we're dealing with negative exponents, we're dealing with 0 exponents, if there's no parentheses, then the answer is probably going to reduce to a negative 1. If there is a parentheses, the answer is probably going to reduce to a 1. And that's likely to make your way, it could make its way onto your test. So I could sneak a problem that has a negative and a 0 exponent, and If it has letters, like if I made a part F and a part G, you're going to need to know if the answer is 1 or -1. And again, these two problems kind of parallel these 4 problems. This one would be a -1. This one would be a +1. If the negative's not in the parentheses, that really means take the only thing that's being raised to the 0 power is the thing that the 0 power is next to. In this case, the x. So this means -1 times x to the 0 power, which is -1 times 1, which is -1. So make sure, even though my review only had the part A and part B for number 2, that you can differentiate between problems that have negatives to the 0 power with and without parentheses, because they give you different answers. 3 is still from section 4.2, and it has all the things with negative exponents. For part A, I'm going to rewrite the answer with positive exponents and simplify the best I can. When I have no adding or subtracting, it's easy to work with negative exponents. I'm going to move the x to the -5th from the denominator to the numerator. And when I move it from the denominator to the numerator, I don't have anything left in the denominator, so I don't need to write a fraction anymore. When I move it from the denominator to the numerator, it gets multiplied by what was in the numerator. And 1 times x to the 5th is just x to the 5th, because 1 times anything is itself. So for an answer to part A, I would write x to the 5th. Part B I'd probably do on my calculator, but I'm going to do it by hand and then check on my calculator. For part B, a negative exponent outside a fraction, you can make that negative exponent positive if you take the reciprocal of the fraction. And now to cube a fraction that doesn't have any adding or subtracting in it, you have to cube each item in the parentheses. So to get rid of the parentheses, I have to cube the 5 and cube the 4. If I didn't know what 5 cubed or 4 cubed was, and I had to use my calculator to calculate one of those, then I might as well use my calculator to do the whole problem. The 5 cubed in the numerator comes out to be 125, because 5 times 5 times 5 is 125. And in the denominator, 4 cubed is 4 times 4 times 4, which is 64. So if I want, this is 5 times 5 times 5 over 4 times 4 times 4. Let me check this on my calculator to make sure my calculator gives me 125 over 64. So I'm going to go parentheses, fraction, 4 over 5, close my parentheses, exponent, -3, and I get 125 over 64, so I'm feeling really good about my work. And I think the answer is correct. On C, I have negative exponents in letters, so I can't do this on my calculator. I'm going to move the y to the -3 up and the y to the -2 down to make their exponents positive. Now I have nothing but positive exponents, so I can use the rules from section 4.1. And I'm going to subtract the exponents. And the y doesn't belong in a denominator, and I shouldn't get a fraction anymore. If the larger exponent's in the numerator, you subtract the exponents and your answer is not a fraction anymore. When I subtract the exponents, I get y to the 1st power. I likely wouldn't write an exponent of 1. I'd probably just write y. I should sneak an extra problem in here. I don't know what letter to give it. It's not in the review, but I often put something like this on your test. So if I gave you the same problem, y to the -2, and tweaked it just slightly over y cubed, that's not going to be, it shouldn't reduce to the exact same answer of y, and it's not harder, but it's easier to mess up. So when I'm rewriting the problem to get rid of the negative exponent, the only thing that's going to move is the y to the -2. It's going to work its way from the numerator to the denominator. The y cubed doesn't get moved because it doesn't have a negative exponent. If I moved it up to the numerator, it turned into y to a -3. So I've moved the y to the -2 down to the denominator. Now I have nothing but positive exponents, which is good. but I have a fraction without a numerator. I can't write a fraction without a numerator, so I leave a 1 behind in the numerator. And now in the denominator, I'm going to add the exponents on the y's and get y to the 5th. So the answer to this extra problem that's not on the review but could be something that is like a test question would be 1 over y to the 5th. Part D, again, I'm given a problem that doesn't work with my calculator because of the x in the problem. So first thing is, if I have a negative exponent outside a fraction, I take the reciprocal of the fraction to make the exponent positive. It would be illegal to move this negative 3. That's a negative number, not a negative exponent. I could only move letters or numbers that have negative exponents, not negative numbers. Now I'm going to cube everything. So I'm going to cube the 2. Don't really need to have the 2 in the parentheses because it's not negative. On the x, I need to multiply the exponent by 3. Technically, I would multiply the exponent on the 2 by 3 because it had an exponent of 1, and 1 times 3 was 3. Similarly, I need to cube the x. Really, I'm multiplying the exponents by 3 because on the 2, 1 times 3 gives me a 3. On the negative 3, 1 times 3 gives me 3. I'm almost ready to write my answer. But the algebra is going to give me a negative in the denominator, and I don't like that so much. So in the numerator, the 2 cubed is 2 times 2 times 2, which is 8. That I could do on my calculator if I didn't know it. 2 cubed is 8. The 2 times 3 for the exponent on the x is 6. And in the denominator, negative 3 quantity cubed is going to be negative 27. This would be okay for an answer, but it looks odd to have a negative in the denominator of a fraction when it's just a single number. You can move that negative up to the numerator, or you could write it to the left of the fraction, and it would probably be better. So all of these are okay. And this is the one I'd probably write on my key. A lot of texts would write that one. For whatever reason, they write negatives to the left of fractions rather than attaching them to the numerator or the denominator. And the least desirable, but you'd get full credit for, is leaving the negative in the denominator. It's just not common to leave a negative monomial or single negative number in a denominator when you don't have to. The next problems I'd probably just do on my calculator, because if I don't know them. I could do them with factor trees, but they're perfect square roots and perfect cube roots. A is asking me what number times itself is 121. I have that memorized to be 11. If you don't have it memorized, you can just do it on your calculator. And the answer to part A is just the number 11. Part B wants me to do the cube root of negative 64. I can do this with a factor tree, but I don't have to because it's a perfect cube root. So if I get a radical on my calculator, I should probably see if my calculator could handle it for me, at least for a perfect one. And the cube root of negative 64 is negative 4. Each one of the 3 problems on the test, I know in my head, and I imagine, I don't know, half of you probably could do them just by looking at them, because you know that the square root of 121 is 11, the square root of 64 is 4, the cube root of 64 is 4, and the cube root of a negative number is a negative number. And then the last one, I know the square root of 49 is 7. This means negative 1 times the square root of 49 when the negative is written to the left of the radical. So this really means negative 1 times 7, which is negative 7. Again, on my calculator, I could just go negative square root 49, and I get the negative 7. For question 5, it has a part A and a part B. On the test, there's probably going to be 2 separate problems, and I don't need to do anything but find the domain. In the section that had these questions, for some of the problems, I sketched a graph and made a table of values. Those aren't necessary. I should know that there's algebra that's necessary to find the domain of a square root. And part A is a square root. If this was a cube root, there wouldn't be algebra. We take whatever under the radical, which I call the radicand, and set it greater than or equal to 0. So there's algebra needed to find the domain of a square root. There's no algebra needed to find the domain of a cube root. And if you do any algebra, like for part B, you'd probably get the number 2, which has nothing to do with the domain. It happens to be an x-intercept. So if on your test you're asked to find a domain and you see a radical, you have to look at the index. If it's a cube root, there's no algebra, and the domain's just negative to positive infinity, or all real numbers. If it's a square root, so it's applied to there, there's algebra to do. So by hand, to do part A of number 5, to find the domain of any square root, I take the thing that's under the radical, set it greater than or equal to 0, and just do the few steps of algebra to take me from this inequality to the answer. I add 3x to both sides, or 15 to both sides, and then I divide by 3. And this reduces to x is greater than or equal to 5. That's probably what I'd write on my key for the domain for this. So you can write as an inequality. The instructions say write as an interval, and to represent numbers 5 or bigger, that would be a square bracket on the 5. Square bracket includes the number, and anything bigger than 5 is from 5 all the way up to infinity. So these are both sufficient answers for me, even though the instructions say write your domain in interval notation. If you gave me the inequality of x greater than or equal to 5 for part A, that would be fine. For part B, it's a cube root. The domain's going to be negative to positive infinity. Round parentheses are appropriate. If you wanted to use words, in words we'd say the domain is all real numbers. Almost every semester I ask a question that has you find the domain of a square root and the domain of a cube root in almost every semester, more than half the class. So I would guess there's like 26 students, 25 students left right now in this class. I would guess of the 25, 18 students will make this mistake and show a 2 in their answer if this was a test question to the domain of a cube root. Most students get the domains of square roots right, but they want to do cube roots the same way as square roots, and that's not the same. If you need to, you can review the video. It's in section 4.3, kind of in the middle of that lecture. I did a bunch of domains with square roots and cube roots. 6 is a friendly problem. I did a lot of prime factor trees to reduce square roots and cube roots and fourth roots. For letters, anytime the exponent is divisible by the index, the simplest way, the easiest way to reduce, to get rid of the radical, is just to divide. So if I can divide the exponent divided by the index and I don't get a fraction, that's the best way to reduce with a letter. And so the answer to part A of number 6, I just divide the exponent 12 by the index 3, and that takes me to x to the 4th. Part B, this really means -1 times, and this means -1 times the square root of x to the 8th over the square root of 64. I have to do the square root of both x to the 8th and 64. The x to the 8th is under a square root symbol, so there's an implied exponent of 2, or index of 2. I'm going to divide the 8 by 2 and get -1 times x to the 8 over 2 over, and then the square root of 64 I'll just do on my calculator. So here the square root of 64 is 8. You can't see it, there it is. So I'm almost ready. So this means -1 times x to the 4th over 8. This is a correct answer, but oddly written. this negative 1, I can multiply negative 1 times x to the fourth and write negative x to the fourth over 8. Or I can just leave the negative without the 1 to the left of the fraction times the x to the fourth over 8. So these are both correct answers. I'd have a tendency to write the one in the numerator. Most textbooks would probably write the one that the top one would be what I'd normally write. The bottom would probably which most authors would write. You could even leave it like this. I'd live with it. It's just not written as simply as it can be written. C, I need to do the cube root of negative 27. I probably use my calculator for that. And then I need to do the cube root of x to the 12th. And I need to do the cube root of y to the 6th. The cube root of negative 27 asks the question, what number times itself 3 times is negative 27? If you don't know that, you can do it on your calculator. So I'm going to do that on my calculator. The cube root of negative 27 is negative 3, because negative 3 times itself 3 times is negative 27. So I'm going to get a negative 3 first. And then for the letters, because they're exponents, when you divide them by the index, you don't get fractions. That's the best way to reduce the letters. So for a final answer to part C, I'm going to have a negative 3. The exponent on the x is going to be 4. The exponent on the y is going to be 2. I'll do the 7s by hand. I'm going to check them on my calculator. So if I have a fraction exponent and I want to figure out what it equals to, I'll make the fraction exponent into a radical. And then I'll do the cube root and then square for this problem. So to get from the problem to the answer, I can't do fraction exponents in my head, so I make fraction exponents in the radical. I know the cube root of 27 is asking the question, what number times itself 3 times is 27, and that answer is 3. So I can do the cube root of 27, haven't done the square yet, leave the square, and 3 squared is 3 times 3, and my answer to this is going to be 9. I'm going to go ahead and double check this on my calculator to see if 27 exponent fraction 2 over 3 power, make sure that that equals to 9, and it does, so I know I haven't messed up. 8 has a negative exponent. I'm going to make the negative exponent positive by writing this as 1 over 27 to the 4/3 power. I don't do well with fraction exponents, but any fraction exponent could be made into a radical. So I'm going to make this 1 over the cube root of 27 to the 4th. And by hand, I'm going to do the cube root of 27 first. And then I'm going to raise to the 4th power. The cube root of 27 is still 3. So this is 1 over 3 to the 4th. And I know 3 to the 4th in my head. If I had to do any one of the steps with my calculator, because I didn't know what the cube root of 27 is, or I didn't know what 3 to the 4th is, I might as well do the whole thing on my calculator. So 1 over 81 should be the answer. And I'm going to double check myself here. So I'm going to go 27 exponent fraction negative 4 over 3. And hopefully I see 1 over 81. And perfectly I do. Part C has a negative exponent outside of a fraction. If I'm working this by hand, I take the reciprocal of the fraction to make the negative exponent positive. 64 over 1 I can just write as 64. I don't really need to write that as a fraction because I don't need to write a fraction if it has a 1 in the denominator. And then I don't really even need the parentheses anymore. Should have written a positive 3/2 here though, because when I take the reciprocal I change the negative exponent to positive. Now I'm going to write it as a radical. This is going to be the second root, or the square root of 64 cubed. Second root and square root mean the same thing. And by hand, first I'm going to do the square root of 64, and then I'm going to cube. The square root of 64 is 8, because 8 times 8 is 64. And 8 cubed is 8 times 8 times 8. If you don't know that and have to use your calculator, then you might as well do the whole thing on your calculator. 8 times 8 times 8, I believe, is 512. Let me make sure that 8 cubed is 512. And it is. Can't see that. Let me do this on my calculator to make sure I haven't messed up. So parentheses, fraction, 1 over 64, parentheses, exponent, fraction, negative 3 over 2. That looks quite a bit like the original problem, other than my fraction's going a little bit different direction, but it's still the same. And I get that 512 again, so I feel good about that answer. 8 wants me to write it with positive exponents only. Part A, because it doesn't have letters, I could do this on my calculator. I'll do it by hand first. On 8, I'm multiplying with two things that have bases of 3. And when you're multiplying with like bases, you add the exponents and don't change the bases. So to do this multiplication by hand, I'm going to add the exponents. To add the exponents, because they're fractions, I'm just adding the numerators of the fractions. So this is going to be 3 to the 1 plus 5 over 3, or 3 to the 6 thirds. 6 thirds is 2, so this whole thing reduces to 9. I believe my answer is going to be 9, and I'm going to double check myself to make sure that 3 exponent fraction 1 over 3 times 3 exponent fraction 5 over 3 looks enough like the original problem. Hopefully when I hit enter I get 9, because that's what I think the answer is. In perfection I get the 9, so I haven't messed up. B, I can't do so well on my calculator because of the x's. I don't work with negative exponents so well, so I'm going to make the only negative exponent positive by moving the x to the negative 1/2 from the numerator to the denominator. The 4 doesn't get moved, nor does the x to the 5/2, because I don't clearly see a negative exponent attached to the 4, and I don't clearly see a negative exponent with the x to the 5/2. So the only thing that gets moved is the x to the 1/2. Now the x's in the denominator are on the same level, so they're being multiplied. So to make the 2x's down to 1x, I add the exponents on the x's. 5/2 plus 1/2, you add the 5 and the 1 and get 6/2. So I get 4 over x to the 6/2, and that's going to give me an answer of 4 over x cubed. Part C, I've got a little flexibility in terms of how I go about simplifying it. I could do the 4th power, or I could simplify the inside of the parentheses first. I'm going to go ahead and simplify the inside of the parentheses. The 2 y's inside the parentheses can be made into 1 y if I add their exponents. I don't care to add fractions in my head right now, so I'm going to just do that. 1/2 plus 3/4 is hardly worthy of a calculator. But 1/2 plus 3/4 turns into 5/4. So I'm going to rewrite this as 2y to the 5/4 to the 4th power. For the 2, it has an exponent of 1 that I'm going to multiply by 4. I'm going to get 2 to the 1 times 4 power, which is 2 to the 4th. And for the y's, I'm going to take its exponent and also multiply it by 4. Again, I can do that on my calculator if I'm not good at that. So for the exponent on the y, it's 5 over 4 times 4. When I do 5 over 4 times 4, I get 5. So in my answer, the exponent on the y is going to be 5. The number 2 to the 4th, if you can't do it on your calculator, it's 16. The things I cheated on my calculator, I did 1/2 plus 3/4 on my calculator. If I didn't have a calculator, I would have multiplied the 1/2 by 2 over 2 and made this 2/4 plus 3/4. That would take me to the 5/4. And the other thing I did on my calculator is 5/4 times 4. If I didn't have a calculator, I'd call this 5/4 times 4 over 1. and I'd cancel the 4's, and I'd get 5 over 1 times 1 over 1, which is 5 over 1, which is that 5. So I could have got the answers with my using the fractions on my calculator, but it's a lot easier to press buttons than it is to do this little algebra or arithmetic. On 9, I should probably tack on a part B, C, and D. So this is another kind of problem that when I put it on the test, like those problems that I did with the zero exponent, that tons and tons of students make a common mistake. So the instructions, write with a radical notation, means I need like a square root symbol or a cube root symbol, and the difficulty is knowing whether the number for these things goes outside of the radical or under the radical. The problem that I have written, if I want to write this as a radical, the only thing that goes, the thing that becomes the index is the denominator of the fractional exponent, and the entire 3x to the first power belongs under the radical. So this would be a correct way of writing this with a radical notation. Inside the under the radical, that parentheses and exponent of 1 isn't really necessary. So although this is an okay answer to the real number 9, it's not the best answer. The best answer would be to write this as the cube root of 3x. Of the 3 extra problems that I made up, part C is real similar. Part C, because the number's in a parentheses, if I did this, I'd say this is the second root of 2x to the first power. And I have a lot of things that don't need to be written. If a 2 is not written in the index, it's assumed to be a square root. If you write a 2, it means square root. If you don't write a 2, it means square root. So it's less writing to write it without the 2, so it's better to do it without the 2. I don't need an exponent of 1, and when I get rid of the exponent, I don't need the parentheses. So the real problem 9 and this problem 9c, they're kind of brother or sister problems in that the numbers are in the parentheses. The next two problems I want to do are B and D, which could just as well be on your test. And for these, you have to separate the number from the exponent, because the only thing the exponent applies to is the x in both parts B and D. So when I go to write this as a radical, it becomes 2 times the square root of x to the first power. The 2 doesn't belong under the radical because the radical only, the exponent of 1/2 only applies to the x, so the x is the only thing under the radical. So if I don't have a parentheses, I'm not going to get a number under the square root or cube root symbol. And I can clean this up and just write it as 2 times the square root of x. If you don't write a 2, it still means square root. If you write a 2, it means square root, and exponents of 1 aren't necessary. Similarly, this part D, the 3 doesn't belong under the radical. So it's super important when you go to take the test, when I given a problem that says write the expression in radical notation, to be able to be 100% certain whether the number belongs outside or under the radical. If the number's inside a parentheses, it goes under the radical. If the number's not inside a parentheses, it goes outside and to the left of the radical. Almost guaranteed that you'll see one or both versions of this. And like I said, it's like a 50-50 proposition on the test. Half the class will miss it, half the class won't. Will get it right. And I think it's just blindly guessing. So make sure that you understand the difference when you're writing something that has a fraction exponent and turning it into a radical. Make sure you understand what exactly goes under the radical is a big deal in terms of points on the test. For 10, there's multiple ways to do it. Probably the nicest way to do it, to turn something from a radical into a fraction exponent. This asks me to write a fraction exponent because rational means fraction. I'm just going to divide all the exponents by 3. So probably the nicest way to do this is just to do that. And then I can tell both the a and the b are under the radical because something has a fraction exponent. When I unwrap the fraction exponent, I get a radical. And that would probably be the nicest way to do number 10. (11), I'm asked to multiply 2 square roots in part A. When I multiply 2 square roots, I get another square root. What I have to multiply here is 3x times 27x. To do that, you multiply 3 times 27 and x times x. 3 times 27 is 81. X times x is x squared. 81's a square root that I know, but if I wanted to do the square root of 81 on my calculator would tell me that that's a 9. And for the x, because the exponent is divisible by the index, the exponent is 2. The index wasn't written, but it's assumed to be 2. Anytime you can divide an exponent by an index, that's the best way to reduce a letter. And I'm going to get x to the first power, which is 9x. I don't need to write the 1. And so the best answer for 11a is just 9x. Part B is another multiply and simplify. When you multiply 2 fourth roots, you get another fourth root. And what I have to multiply is a to the 5th, b to the 1st, times a to the 7th, b to the 11th. To do that multiplication, you have to multiply the a's by adding their exponents. You have to multiply the b's by adding their exponents. So the multiply part of the multiply and simplify is going to give me a to the 12th power, b to the 12th power. This is 1 plus 11 and 5 plus 7. And again, if the exponent on a letter is divisible by the index, the nicest way to drop the index, or the radical, should I say, is just to divide the exponent by that index. So for an answer to this problem, I'd get a to the 3rd power, b to the 3rd power. There are other ways to get to that answer, but none that are significantly better. Part 12, I usually put one of these questions on the first half of the test. The question 12, the skill in it, it's the most important skill from the first 5 sections in terms of it comes up in every section for the rest of the chapter. To do the square root of 50, because it doesn't have a letter and it has a square root, my calculator can tell me what it reduces to. The answer to this, the square root of 50, is supposed to reduce to 5 times the square root of 2. If I wanted to verify my answer by hand, I'd do a prime factoring for 50, and the prime factoring for 50 equals 2 times 5 times 5. And in a square root, anytime you have a pair of something, you get one of those outside the radical, and anything that's not a pair goes under the radical. So the prime factoring will show me the pieces to my answer, the 5 that's in front of the radical and the 2 that's outside the radical. The 5 that's outside the radical and the 2 that's under the radical. If I try to do the cube root of 40 on my calculator tells me this is 3.41995. That's not how we want to reduce the cube root of 40. I want an answer to have a number outside the cube root and a number under the cube root. I want my answer's decimal equivalents to be the same. So I'm going to do the factor tree approach to reduce. I'm going to go 40 equals shift and then that button with the quotes on it. So 40, its prime factoring is 2 times 2 times 2 times 5. In a cube root, anytime you have 3 of a kind, you get one of those outside the radical. Anything less than 3 of a kind stays under the radical. So I think my answer is supposed to have a 2 to the left of the radical and a cube root of 5 under the radical. I'm going to check, and specifically, I'm going to do the decimal equivalence, and it has to be the same 3.41995. If it doesn't equal the same decimal as the original problem, then I've messed up. So I'm going to go 2 shift cube root of 5, and I see exactly the same 3.41995. So I feel really good about the answer. It must be correct. Last problem, I'm going to treat this as 4 separate problems. I'm going to reduce the square root of 27. I'm going to reduce the square root of x. I'm going to reduce the square root of y to the 6th. And I'm going to reduce the square root of z to the 7th. Square root of 27 I could do on my calculator. Square root of 27 would have a 3 outside the radical and a 3 under the radical. If I didn't want to do it completely by my calculator, I could do a prime factoring for 27, because 27 is 3 times 3 times 3. The prime factoring tells me I have 1 3 outside the radical because I have a pair of 3's, and 1 3 left over to put under the radicals because of the other 1 extra 3 left over. The x, because there's only one of them, it doesn't reduce and it stays under the radical, because to get something outside a radical you have to have at least a pair. For the y's, the most efficient way to do y to the 6 is just to divide the exponent of 6 by the index that's not written but assumed 2, and you'd get a y cubed, and no y under the radical. If you wanted to write down the prime factors of the y's, or expansion of the y, you'll see that you're going to get 3 y's outside the radical, because there's 3 pairs of y's, no y under the radical because there's nothing left over, and the 3 y's outside the radical, it's probably best just to write them as a y cubed. And there's no y left under the radical. On the z, if I took its exponent and divided it by 2, I'd get a fraction. I'm not going to reduce the z the same way. Only when the exponent divides by the index and you don't get a fraction is that the way you want to reduce. For the z, I'm going to write down 7 z's. And every time I get a pair, I get one of those z's out front. So in the reduction for part C of number 12, I'm going to get 3 z's outside the radical, and I'm going to write those 3 z's with an exponent of 3. And the single z that's left over after I write my 7 z's and form my groups of 2, I get that z stays under the radical. So for my answer to part C of number 12, I should get a 3y cubed z cubed times the square root of 3xz. There's only going to be one problem like a number 12 on the test, generally. I mean, unless I change my style. But normally I just write one problem where you reduce a radical on the first part of the chapter 4 test. And then on the next part of the chapter 4 test, you'll get overwhelmed with these, so you'll get to get really comfortable with reducing the radicals. So that's everything that could be on the test from sections 4.1 through 4.5. So if you're getting 2 tests over chapter 4, you master all these 12 problems plus the little extra things that I threw in. Be very aware of what you can do with 0 exponents, whether you have parentheses or not, because that really messes up students a lot. And be aware when you're writing fraction exponents as radicals, like I did when I did the problem 9 and I made the extra ones. Those problems that I took the time to make extra problems, really focus on those, because those are problems that historically half or more of the class misses, and they're not hard, and they're not problems I can give a lot of partial credit. So if you miss these, then if it's a 3-point question, you're just going to get a -3. So the questions with the 0 exponents that we had to rewrite, and the parts that had fractional exponents that we had to make into radicals, make sure you understand how to deal with the numbers and the letters, whether there are or aren't parentheses, or how to deal with the negative with the 0 exponent, whether there are or aren't parentheses. Okay, that's going to be enough. Come visit me if you're not feeling good about this stuff, because it's better to ask right before the test rather than after the test.